network that divides all VCCs to basically provide that switching or signaling control for the uh, various connection within the ATM network. Okay. The other two-level connection that you have within the ATM is the virtual path. Okay. Okay. Before that, let me relate a VCC to in a much more practical uh, logic for visualization purposes. A VCC would probably be, which is the logical connection of an ATM, the main logical connection of an ATM, probably be like lanes of on a road that are providing a road segment for cars to move through. So if you're on a road, you have various lanes, right? So those various lanes can be considered as the VCC or the virtual channel connection of an ATM. So that's to base in a way to give you a picturesque view of it, of how ATM VCCs might look like or might virtually look like to you, using roads as an example. The virtual path connection, on the other hand, it's a bundle, or it's usually used to bundle the VCCs into one single route for cells uh, to flow within, or for cells to carry data feeds or data transmission across. So if you want to relate to the picture of a road again, the VPC, or the virtual path connection, will probably be the road itself with lanes or with the VCC on them. So the road will be the virtual path, and the lanes will be your VCC. Okay. Some of the advantages that the VPC, which is your virtual path connection, serves includes simplified network. It simplifies the networks. Uh, it also improves the simplicity of the network architecture to allow for transport functionalities to exist in a calmly order. It also increases network performances and reliability. So at least we can handle fewer and aggregated traffic elements within the given transmission. It also reduces processing and short connection setup time to enhance network services. Okay, so these are some of the key advantages that the virtual path or the main road provide for the lanes. So let me go over this again. One, it creates a simplified network architecture for transport functionalities. It increases network performances and reliability, mostly for fewer and aggregated traffic elements, and also reduces processing and short connection setup. In terms of time, when it comes to time, and then also enhances network services. So here we probably want to look at a typical design of the virtual connection, or an ATM virtual connection. In this case, looking at it from a physical link for fiber optic, as a fiber optic cable, or and it's if you want to look at it from a physical point of view, you do have the physical link itself with the virtual path. So a virtual path within the physical link, and then within the virtual path, so it's a roads, and then within the roads you have lanes, which consist of your virtual channels. Okay, so you have VCCs occupying or bundled up, as we mentioned earlier, bundled up within the virtual path. Vast majority of ATM networks runs on fiber optic networks with extremely low error rates, and also supports low cost attachment. Okay. Great. Now here's uh, more or less a routing table within an ATM switch. So when we look at ATMs and their logical connections, their virtual connections, virtual channel connections, and then virtual path connections, how do they really formulate and handle the transmissions that comes through? So in a display, we have something like this. We have this ATM switch with one, two, uh, one, two, three virtual path coming in on the inlet or on link 5 in this case, and then 3 on the outlets. So going out, coming in, or in and out, and they both have 3 key virtual path or three key roads, and within those roads we have each road or one of the roads. In this case, the virtual path has 2 lanes of 2 virtual channel interfaces, which is virtual channel 2 and virtual channel 5 for virtual path interface 1. And then for virtual path interface 3, we have only 1 channel coming through, channel 9. And then for virtual path 5, we do have 2 channels coming through, 4 and 6. Okay? And then now depending on the traffic flow, it's the job of the ATM switch to reroute the channels from the inlet of a given virtual path to an outlet of a given virtual path. And it all depends on how much information is coming through. If the switch realizes maybe cells from virtual path uh, are too overwhelming and needs to be or are prioritized and needs to be routed on a much more less congested path on the outlet side, in this case link 10, then it can reroute a given channel from a given path to a different path. So if you notice with uh, with path 1 having 2 and 5 channels, you notice that one of the channels got rerouted to a different path. In this case, a virtual path interface 7. So it's 2 that was let out, was switched to virtual channel 2 here. If you look at 2 showed up on this side. So 2 was switched on this side and then handed over to what? Virtual path interface 7. Okay, so let's go through the routing table in terms of how the information flows, comes in and goes out, and how it's switched back and forth within the inlet and then outlet, or incoming and outgoing. For links 5, is link 5, which is the inlet, or inlet, the incoming is having, it's holding link 5, and then outgoing is having, it's been labeled as link 10. And within the incoming link, we do have virtual path 1, 3, and 5. 1, 3, and 5. For the outgoing, we have virtual path 3, 7, and 8. Now, within the incoming, virtual channels for path 1, we had channel 2 and 5. So path 1, 2, and 5. For path 3, we only have channel 9. And then for path 5, we're supposed to have 4 and 6, but I'll get to why it's a dash away here. Okay, now let's look at the outgoing. The outgoing we have for path 3, we have channel 1, which was probably switched from path 1. And then we have for path 7, we have channel 1 again, so multiple channels. And then same path 7, we have channel 2, and then for path A there was nothing. And the dash represents, this is why we have dashes, usually within an ATM switch when an incoming link or path forwards channels directly across without switching like it did for 1 and 3 to 7 and to 3 and 7. When usually that happens, we say there are no virtual path interface established or created for that particular transmission switching. So when it's true and true, we indicate a dash, indicating that the channels were not switched basically. Unlike the 1 and 3 and 3 and 7 path, the channels were switched. They had to take out various values. But unlike 5 and 8, since they are directly connected and there was just a through and through transmission, we say there are no virtual channel interface established or created for transmission. And let me go over how a given ATM relays information back and forth across a given medium or a given network. So usually when information comes through, there's a request by the VCC to request for a VPC. So a VCC originates, a request originates from a VCC requesting for a path or a lane request for a path to transmit information. Now, if a path exists, so this is a flow diagram, not a context. This is a flow diagram. So a flow diagram of how an ATM really switches information or hands information back and forth from the VCC to VPCs. Okay, so the first request is coming from, it's actually originated from the VCC requesting for a path, and if a path exists, then and the quality of it be guaranteed. If it maybe depending on the capacity of that information, the VPC usually have to ask that question from the VCC request. Can I guarantee the quality of the service that you're carrying? If I were to handle the transmission, if the VCC agrees, then would allow the information to. Then in that case, say yes, it makes a connection or establishes a connection for transmission to go through. Okay, so that's if it's a yes, yes. Now, if it's a no, then it needs to find, and then the first VPC that was contacted or that request got to needs to request or establish another VPC connection within the ATM switch, requesting for a different VPC that can carry the traffic or that can identify a given quality needs of a given VCC request. Okay, so once that is established, then it goes back to the quality part. Can I guarantee or satisfy your quality of service for that VCC request? If it's a yes, then as usual, the connection is made. Now, what if the quality of service is not satisfied? Then in that case, the VPC blocks the VCC or requests more capacity to handle that particular transmission service that's coming from the VCC. And when the request comes through and it's granted, then it makes a connection. If not, then the VCC is rejected, basically. So this diagram is coming from a textbook. You can look it up. Okay, you can just follow through how some of these transmissions are handled in terms of the flow of request that comes through. Okay, so that should be the flow diagram of how ATMs handle their request in terms of switching for the VCCs or between the VCCs and VPCs. How the ATM routing table is addressed or handled. And here I do have some various ATM devices that I came across from some of the labs or data centers that I visited. So I took pictures of them and I'll capture some of the images of them to show you guys. There are a whole bunch of ATM and switching devices. Look at the breakdown of a typical ATM cell format from the user network interface point of view, so we can identify how the header informations have been allocated in terms of bits and their various names. So the first one we have is within the header. Remember the header had about 5 octets, which is 40. So 5 times 8, 40 bits in all. The first one within the layout of the header part of uh, the ATM cell format. We have the generic flow control, which has 4 bits. We do have your virtual path interfaces, 4 on each side, so making up 8 in all. And virtual channel interfaces 4 bits with additional 8 bits at the third column of the layout, making 12 bits in all. We also do have on the fourth level, we do have a virtual channel interface, again, 4 of them. So if you look at it carefully, in all we have about 4, 4, 8 for the virtual channel interfaces, which is about 16 in all. So we got 16 in all for that part, and the path is only 8. We only have 8 bits for that, and that pretty much actually does make sense, because we need a lot more roads, so a lot more lanes in a road, basically, if you want to look at it from that point. Yeah, you need a lot more lanes in the road than just a lot more roads without lanes, or the other way around. So hence the reason why you have 8 bits for the virtual path interfaces, which are the roads, and then you have 16 bits for the lanes or the channel interfaces. We also do have the payload type, carrying the type of payload that it is, depending on the type of data that you're carrying. There has to be a type to it, and it's been allocated with three bits. Basically, identify if it's the video content, the type of format. So that has been allocated with 3.3 bits. And we do have 1 bit for cell loss prioritization. So in case there are errors, that can be easily communicated back. And as usual, you have the huge chunk of the ATM cell format carrying the payload or the load itself, the data itself, which is 48 bytes or 48 octets. So that pretty much tells us about how the cell formats, it's well distributed at the cell header part, or the cell header segment of the format. Now let's move on to the protocol architectures, or in terms of its layout, to address how information is routed or switched within the various ATM LAN, from even a terminal point into the ATM LAN itself. Okay. Um, so here we have the layout of it. Uh, We have in this case we have the endpoints or ATM endpoints, which could be your various terminal devices that are connecting to an ATM switch. So you got the kind of like an incoming terminal into an ATM switch and an outgoing terminal into ATM switch. And ATM, it has got three key layers, um, kind of like the OSI model with 7 layers. The ATM has got its own layers. In this case, 3-layered architecture for handling its protocols. The highest layer is the adaptation layer. That's probably where you carry a chunk of your data itself. And then you do have the actual ATM layer and the physical layer. Physical layer here relates to more or less the physical medium from the fiber optics, or if it's a coaxial cable, or if it's a twisted pair cable. But generally, the physical medium through which the end device or terminal connects into the ATM switch. And then within the ATM switch itself, we have 2 layers, 2 key layers. Okay, let me go back. The terminal within an ATM uh, device setup would have 3 layers. The ATM switch itself would have only 2 layers, which is the ATM layer itself and then the physical layer. So keep that in mind. The endpoint device or terminal device that connects into an ATM switch would have 3 layers because they're basically the ones carrying the data. So you do have the adaptation layer to address that part, and then the 2 additional layers that forms more or less the ATM switch itself. Okay, so if an information breaks comes into the from the ATM terminal, it goes through adaptation layer. Like with the OSI, it goes from application layer all the way to the physical layer. In this case, from adaptation layer to the ATM layer itself, and then the physical layer. This way, it basically exits the information, and the cells exits out of the endpoint device or terminal, and then as you just the reverse structure going into an ATM switch, it goes through the physical layer first to the ATM layer to identify the kind of cell being transmitted, and then it finds out which uh, uh, path to use or which series of channels needs to be rerouted or re-switched to different path on the outgoing end. And then once that is addressed, it basically hands it off out to uh, the next hop on a device transmission, or the next device at the other end. And then the formation just continues the same process again. It goes from the physical layer, the ATM layer, and then adaptation layer, where the user actually gets the data itself. The terminal receives the data itself. Okay. Okay, so let's look at the description of some of these layers that we have, starting from the physical layer here. So we're gonna go from bottom to top, I guess. The physical layer is actually the lowest layer in the ATM protocol, and it describes the physical transmission medium, obviously, like the fiber optics or coaxial or twisted pair cables or whatever you have. But that basically uh, relates to the usage of more or less the physical medium itself for transmitting information. The ATM layer, which is second layer, it performs all function that relates to routing and basically multiplexing, kind of like how we group the various cells in their bits to be sent over to the physical layer for transmission. So the job of the ATM layer is to perform all the function that relates to routing and multiplexing of the cells over the virtual channel that we have. It also generates and move headed content destined to a given adaptation layer. And as far as the other role that the ATM layer plays, it maintains a table which contains a list of all the various virtual channel interface that we have, or more or less like the routing table for an ATM. Great. And then the adaptation layer would probably be the top layer that we have. That's where more or less the um, it's information or data converts the submitted informations to the various streams that you have of 48 octet segments into the payload, uh, and then transport these in the payload field for various ATM switches that needs to carry the information across. So basically converting the submitted information into streams of 48 octet segments and transport these in the payloads fields of multiple ATM cells. They also defines it's also defined into five categories or five classes, which is more of a breakdown in terms of how the adaptation layer handles the conversions of submitted information. So there are five classes, which is from ATM adaptation layer 1 to 2. Those two layers handles the connection arrange services for your constant bit rate, constant bit rates, and variable bit rates that we have within a transmission. And then the last three, which is from 3 to 4, provides the non-real time bit rate service that we might have, like your data services. So in this case, you would say your adaptation, so ATM adaptation layer 1 and 2 would provide for the constant bit rates type of information, and then for the variable bit rates, you'd have your video conferencing, on-demand video streaming, pay-per-views, what else? The number of data that just doesn't require that constant bit, but instead can be in a variable. You have your T1 connections, your um, telephone connections, and then for the real time with variable bit rates, you do have your video conferencing and uh, other video services that you might have, or streaming services that you might have, either pay-per-views, on-demand video streamings, and what have you. And then for the non-real-time variable bit rates, you do have your multimedia emails, which is where you do have content that you're accessing that are not in real time. Okay, so those would have the non-real time variable bits. So you have emails, browsing, transfer of files, background files, and whatever you have. Those are covered within the non-real time variable bits rates. Okay. Now on the issue of services that ATM provide, since you want to guarantee a better service within a high capacity transmission like or packet switching like this, you definitely want to put together some key measures that relates to quality of service, and that's where we talk about the various requirements that deals with the quality of service or QoS part of the ATM. So in this case, we're looking at requirements that handles connection time and uh, and viewed as part of the signaling transmission of a given ATM cell transmission. ATM would provide the permanent virtual connections and switch virtual connections as well. The permanent virtual connections are the PVC, which is set up manually by network managers when they're basically handling the connection setup for a given installation or a given client. Yeah, and then you have your switched virtual connections or the SVC, which are set up and released on demand by the end users via signaling procedures that have been implemented on either the terminal or the ATM switch itself. Okay, so now we look at other challenges that goes with the with ATM. Of course, just about any other uh, uh, switching technology. In this case, a packet switching at its evolution stages. When it comes to ATM, there are bound to be some other challenges. You know, the extra 2025 standard had challenges, so they had to basically upgrade it to the frame relay, and frame relay also had its own challenges, so it was upgraded to ATMs and ATM to Sonet, Sonet to other technologies that we have today. You know, so yeah, so let's look at some of the challenges that ATM poses to uh, a given network transmission that you might have. The most widely known challenges could probably be cost. It's an expensive system. If you go back to look at how many devices involved, these are extremely expensive devices that we have. They're extremely expensive, bulky, requires complex configurations. Uh, that overwhelms a lot of engineers, you know, from back there. It's not as simple as today's, you know, configuration of various routers and switches that you have to address your packet switching needs. Those were this required complex implementation. That's quite grueling back in the day. If you were an engineer back in the day configuring ATMs, you really had your work cut out for you. So that was probably one of the biggest challenges that goes with it. Um, I'll probably say another one will probably be the uh, uh, what else can I point out? That's looking at the um, maybe how it interconnects with other devices. Even though one of its goals of implementation revolved around interoperability. Yeah, I got the word right this time around. Huh? Yeah, but it still lagged behind because other implementation came up which had problems or challenges trying to adapt or trying to incorporate or integrate with ATM system or ATM implementations. So okay, your ATM has not been widely accepted, although some phone companies still uses them. The whole, not today though, not today. Uh, but back then, mostly used for your backbone networks. And as I pointed out earlier, yes, it was the expenses was one of the key challenges that goes with the ATM implementation, the complexity as well, and then lack of interoperability with other technologies. Kind of prevented ATM from becoming more of a mainstream prevalent technology for addressing packet switching needs. Even they could carry a whole lot of data. It was highly capacity wise. It was highly uh, appreciated because it could carry that much high data capacity. But other issues that arise is kind of really prevented from being the prevalent technology for addressing our service needs today. You know, so yeah, every system has challenges. You can't really do much about that. It's just how the way it's basically just the way the cookie crumbles, I guess. Sometimes you'd have short ends. It's about anything that you want to put together or that you put together. You want to have some short ends. It's not going to be all that perfect. It's a system. The technology happens to be evolving on a daily basis or what have you. So challenges will come that will basically lead to, people not adapting it or embracing it that much or not moving on to a different technology. So some of these issues did come up within the implementation of ATM uh, technologies. Uh, so when it comes to the expenses, we're looking at the cost. ATM switch alone was quite expensive hardware. they cost a lot more than your typical average LAN hardware uh, owned at various subscribers' locations. In addition to a network interface card needed to be connected to a computer to an ATM network, which means significantly more expensive than corresponding NIC interfaces. Keep in mind that ATM had got their own interfaces, either a user network interface for user to connect to an ATM network, or a network to network interface for another ATM network to connect to another ATM network. Keep that in mind. So it wasn't as compatible with NIC, which is your network interface card that you use today for your Ethernet transmission, the one that you have on your laptop, on your phone switches, what have you, or basically on Ethernet technology level. It wasn't compatible, so that created a lot of challenges with the cost for some of these interfaces to be implemented. Connection-wise, the setup and latencies, when we look at the connection-oriented service that it was designed for, it introduces significant delay for distant communication. So which means when you did have long-distance transmission that goes through various other um, networks, you're bound to have all these. It's not every other network that might have the same conformity to ATM or that might have the same ATM implementation. So transmitting an ATM network to various other network being connection-oriented service or design usually creates a lot of significant delay for distance transmission or communication. So yeah, keep that in mind. And then complexity of the quality of service, which is related to specifications that were made to the implementation was quite cumbersome and quite difficult, as I mentioned earlier. It was just too complex. Engineers go through a lot of time just trying to set up some of these devices back then. So it made implementation quite difficult and cumbersome in a way. Carrying around some of those big devices and installing them. It was taking up so much room and all of that. It was just too much. You know. Many implementation did not support the full standard. That's also one key thing. Many did not support the full standard of the implementation. So it all factored into the challenges that ATM had to deal with, which prevented it from becoming mainstream technology for addressing today's service needs that we have. Today we have much more robust, easier, and simpler technologies that's able to addressing a lot more capacity needs than ATM even did. Yeah, I mean, think about some of these technologies today. We have a whole bunch of uh, Ethernet it's quite robust in itself. Very very efficiently designed, addresses your transmission controls, your error controls, signaling, and all of that, handling routings uh, at various levels. And that all, changed the dynamics of how people really looked at ATM. So implementation, design, it wasn't, I mean, you could say that at the time of implementation, it was definitely the best. Obviously, it would carry a chunk of your data for you, high level transmission. It would just handle it with that huge payload, that size that it had. It could address a number of challenges back then. But with time, like I said, technology evolves and newer designs comes up that were much more robust, much more uh, simpler and easier to comprehend, and also cost less. Today, even an individual can own a simple network switch or a network router, right? But back then, owning a router, an ATM switch, you'd have to be either a service provider or really big corporation that wants to run your own ATM network. And today, that's just not feasible. It's not realistic. We need smaller systems that easy affordable. It can easily address our uh, data needs or transmission needs wherever we find ourselves. And this obviously, ATM obviously didn't address that. So it didn't become mainstream. Um, you know. Anyway, so that pretty much wraps it up for the ATM. A lot of readings are involved. A lot of materials covered within the chapter. Um, if you go to the William Sterling textbook, chapter 11, uh, from subchapter or subheading 1 to 5, covers a chunk of the related topics within ATMs. Some of them are very technical. I didn't want to incorporate them into the slides, but if you really want to get into the nitty gritty understanding, you can just read through the textbook and you'd have a broader understanding of how an ATM implementation was done, as an evolution from a packet switching point of view over the years through the standards of an S25 through frame relay and onwards to ATMs. The other evolution on ATM is the Sonnet, which is also another higher capacity transmission that revolves around more or less fiber optics mediums. So all of them are in the textbook that you can read about. But for this particular topic, will just revolve around the evolution stage for the various packet switching techniques that we had. So how it became what it is today that we use for most of our transmission needs. From the X25s, frame relay, and downwards to Ethernet today that we have for most of our implementation needs and protocol base as well. Okay, so that should do it for chapter 11. Okay.